Hello, everyone. Welcome to Zagreb Graph Data Meetup. Today with us we have David and Jan from MANTA. They will talk about tracking data lineage with a graph database. So if you have never heard about data lineage, you will hear what it is and why it is important and what can you do to use your graph database to be sure that all the things that are in line and that you can get the right conclusions from the information that you have gathered. So this lecture will take about half an hour. After that, we will have Q&A session. First, I will read the questions that come through online system. So if you're watching a webinar, please ask any questions that you have in the chat. I will read them out later. And after that, we will move to the Q&A part here from the audience. For those of you that are here in the audience, if you have a question, raise a hand. I will come to you with the mic so the people that are following us over the webinar can hear that question. So that is from me. And now, David and Jan, please take the stage. Thanks.
Thank you for a nice introduction. Welcome, and we are really pleased to speak here on Graph Data Zagreb and introduce our product. So, my name is David Bucek. I'm a leader of architecture at MANTA. Please welcome my colleague, Jan Žák. He's responsible for graph databases in our company. And our company is MANTA. We've arrived here from Prague, the Czech Republic. The MANTA started there. Actually, we are growing a lot, so we have an office in Florida right now. We have office in Lisbon. We have office in Dublin. So, yeah. I'm really afraid that we become a big corporate soon. Hopefully not. Just we still keep this, startup culture. Okay, let's start. Track data lineage with the graph database. The usual question is, what actually is data lineage? We always start with that. So, introduction for that. Data lineage is a detailed map of all direct or indirect dependencies between data. It maybe sounds a little bit formal, but you can imagine that the really big companies, they have 100 systems, and they very likely don't know how they are connected together. So this is the thing we are helping them with. So they are interested in how data actually flows across their systems, how their systems are connected together. Because each system is developed by some team or some even external company or something, and they don't know how it's connected everything together. So mapping of complicated systems. So it's not just this, not just mapping, but we also know how data are calculated. If there is some transformation, on the way, we are able to catch it and show it and manage it, let's say. So we can pick even the instruction of code. We are experimenting of data lineage in the Java bytecode, for example. So to get known the transformation, what's happening with the data. So it's pretty interesting, I must say. So, where are the sources of data for data lineage? We usually have three categories. I'm speaking about this part. the type of data lineage. The first one is a static data lineage. What we do? We usually see the schemas in database, in general metadata, and parse them and try to deduct from this static metadata how they are connected. That's what we really do. That's what MANTA does. Other types are runtime data. So that software could listen some method calls, procedure calls, and gather those data. It could be possible even from log files and so on. We can reconstruct it. And the third type is record data lineage. It's actually listening of the real traffic, and from that real traffic, you're able to reconstruct how the systems are connected together and what is actually happening there. But as you probably feel, this part is extremely data intensive. So the storage then, it's huge. We here in the term of a normal company could be 100 gigabytes, and this, several magnitudes more maybe. So it's maybe something we will be talking about future. All right. So the unique features of MANTA product, it's first of all, the wide range of technologies we are able to scan. Just we can scan the SQL databases, reporting tools, ETL tools, and even some programming languages, as I mentioned, Java, and also COBOL, because our customers are usually big companies, big banks, and they have a lot of code still in COBOL. And with the COBOL, there's one specific problem that a lot of people who actually wrote it, it's retired. Yeah. And the other really unique feature is it's automated. So we can set up our tool, our product, point it to some database, and we are able to extract or harvest all data and store it to our metadata repository. So a lot of things, not all, but a lot of things are really automated. So it really help us, or help our clients to have a whole map of the systems. Otherwise, a lot of them, before they have our product, a lot of them did it manually. Very inefficient. Third thing I mentioned here, it's revisions. So we can keep track of every changes, every system which is configured. Very useful thing, I will explain it in a few slides when I will try to show some real use cases. And if you want to know more, here on getmanta.com, we have ultimate guide to the data lineage. I am pretty sure that it's really nice described there, and it go to the much more details than I mentioned, because there's not enough time. Oh, and here are those use cases. So what is a real use? I pointed out just 3 of them, but we have much more, but those are really useful. First thing is, the bank, insurance company, and so on. Everybody in this area has some regulator. And the regulator arrived to the company and asked the data governance team, OK, let's say GDPR. how can you prove us you deleted all sensitive data about your clients? And usually they don't know, because they don't know where all those data are. But when they have MANTA, and they say, OK, we have our sensitive data or our client-sensitive data on those places, and I can prove you about that we will delete them all. And the regulator usually accepts that. That's fine. The other things, data governance. So they frequently ask how they could safely migrate data or stop one system they don't use anymore. And does this affect somehow the other parts of the system or not? They are not sure. Just in a normal way, they send a couple of emails. To some emails, somebody could reply, and some emails, maybe not. They're still solving this. So if they have MANTA, they could, let's say, simulate. So, OK, so what happened if we turn off this system? Or what happened if we change this interface? Who will be affected and how? So who should we contact that we are doing some change? Useful for them. And other things could be a data operation. So they should know, they could know how the algorithm or how the calculation were changed in time. So what happened? One of our customers, it was some American bank, have a problem. Just somebody arrived to branch and asked for a loan. And it was declined. But the same guy arrived 3 months later, and he was accepted. And he thought, OK, so there was discrimination before, and sue them. And of course, they were a little bit scared. And the judge says, OK, so was it discrimination or not? The bank says, no, we changed algorithm. The judge says, how? And bank, they don't know. But somebody said, OK, we have MANTA. So they should know how we actually changed the algorithm. So they find it in the system, they show it to the judge, and say, OK, there was nothing with discrimination, nothing like that, and they won the all case. So that was like interesting story, like how MANTA could be used. All right, let's move on. So I'd like to show you a really brief demonstration. It's just about one part of our system, and we call it viewer. So this part is like the simplest one and pretty straightforward. So we really try to simplify a lot of things to be able to say it in 30 minutes. So this part on the left, it's a repository tree. It's something we scanned before. So in the repository tree here, or maybe I'll use pointer. Wow. We have technologies we already scanned before. And here is a tree from, if it's like, let's say, Oracle database. So this is schema, this is schema, and this is some table, and table contains some columns. So that's what we scan, right? And I like to, I like to show you the visualization, and then we see. If I like expand it, right, here, here, and so on. So this graph is like pretty simple. It could be like, almost 100 those rectangles, but you see that, okay, we have some export card fees table here, and now let's say we have some product code, and now we see how this is not expanded, but we know how it's connected with other systems, right? And this is like part of, visualization, really, really simplified. My colleague later will show you something else with that, right? So it was just for the imagination. Okay. Now, finally, where is the graph database there? So everything, what you saw there, what you saw before, there is a graph database on the background. So that's our main storage for metadata. I'd like to explain why we picked this technology. The structure what we use, it's pretty simple. That's here on the top, and it's pretty simple and even simplified. It's a resource. The resource, it's let's say the technology we scan, database, or as ETL software, or whatever. Here, we have some assets, which is basically everything what could be in hierarchy under the database, so some tables which contain some, or some schema, some tables, and so on. And here, we call it like a leaf asset, because it has special role in our algorithms and in the schema. It's the leaf of the tree. So it's usually the last let's say, last asset in the hierarchy. So in terms of a relation databases, it's usually column. And in a column, there is stored some information. And this structure, we call it vertical hierarchy of the metadata. So another structure we have in our database, it's the horizontal one, and the important relationships are those direct flow. We have more of them. I'd like to show just this, but principle is the same. So the leaf assets are connected by some flow, which means that from this column, data goes to another column, or another process, or to some reporting tool, and so on. So that's how we simply map the data flow. And actually, it's connected together, like this. So we have the hierarchy here, and connected leaf assets down here. So we can, at the same time, we know how the leaf assets are connected and what's its parent. So to which table they belong, or view, or procedure, function, whatever. It could be like here, it could be like anything, basically. Okay. So here is together, that's colors. Colors mean something. So here on the next slide, I skipped the titles because it's resource, asset, leaf asset. So this is let's say, Oracle database. And this is SAIS ETL tool. And here is mapping. It simple goes between those two technologies. So in our database, all those technologies are connected together by data flow and the leaves. All right. What we scan, how the scanning actually look like. I want deep dive on the parsing of the source code. It's like sometimes it's kind of magic, but we start with the normal SQL code. So with the definitions, schemas, and so on. When our clients ask us, or we ask for some permissions, so we ask them okay, if we want to set up the connection, you need to give us some permission. But we don't need permission for the real data. Just for schema is fine. Everything what we deduct is from schemas. So this is basically enough where we start. Simple create table, also plus all procedures, function, everything in the database we could parse. Then we create simple AST3, which is our middle product. We speak about this on different kind of presentations. If any company or institution invite us, okay, just tell us something about parsing and so on. We really go deep on this slide, but now I think I can skip it. And from the ASD3, we are storing the actual nodes and actual relationship to the database. So it looked pretty similar and straightforward. So how it's parsed and then how it's stored in the actual database. Okay. And this is how we present the final result. So you before saw the screen, so it was actually the same as I showed you before. This is the table which is in all presentation all around. Right. And this is a part I'd like to ask my colleague, and he will tell us something about the differences between graph database and the relation database, because before we used the relationship database, and there's some reason why we move. Okay.
Yeah. Thank you, David. Thank you for your nice introduction into data lineage, and I'm going to tell you now a bit more details about how we started with a relational database and what are the benefits of using a graph database for the data lineage use case. Yeah, previously, even before I joined MANTA, MANTA is a company with I think 7 or 8 years of history. There was a relation database with SQL queries that traversed all the hierarchy that David showed you with recursive queries. That means that each hop in the hierarchy was queried by a join. And if you have a university background, then you should know that each join has a logarithmic complexity. So that means that with recursive queries, it would mean that, where is the pointer? Each join is logarithmic, and well, if it's recursive, then the count of inner joins increases with the length of the relationship chain. This is one of the issues, performance. And even though there are some relation databases like Oracle or MS SQL that have, well, let's call it graph syntactic sugar, so that they can allow you to write graph queries in SQL. We still say it's not a native graph storage. It's non-native because it means that it only simplifies the query for the developers to read and write, but it doesn't help with the underlying data complexity, computational complexity. So when we are going to the graph databases, there is an important feature, a property of them, which is sometimes called index-free adjacency. That means that the data are stored in a way that allows graph traversal in constant time, O1. So we can write these recursive queries without well, with no performance implications. We can go to 20 levels of recursion, and well, it still works performant for the user. And also the traversing in both ways is equivalent in performance. That means with relation database, you could have a, well, the relationship goes usually in a single way, going from top to bottom or bottom to down. But with graph database, we can traverse the relationship in both ways, and we don't lose the performance. And I'm going to show you 2 examples of queries that we have in MANTA. And when we start, the first example is finding the asset hierarchy path in the database structure that David showed you. And let's consider in SQL database, there could be a table like this, table called asset, which has ID primary key and parent ID is the foreign key. And in the actual data, in the second table, we can see that there is a root of the tree is the resource oracle, which doesn't have any parent, is the root of the tree. There is the second line is the table, which is straight below the oracle. It's connected with parent ID and ID equals 1. And there are columns which all have parent ID too. And if we were to write a query, recursive query in a SQL database, there are multiple ways how to do it. You could either use a loop in PL/SQL, or some database has a feature of recursive joins. I'm not sure if you are familiar with the syntax. It can look like this. There are 2 important parts to it. There is the entry point to the traversal. So here I'm choosing the column with ID 6, which is the fee amount. And then there is the part here, which actually performs the recursion because it looks to the same table, and it only stops when it reaches the Oracle technology because it has the null parent ID, so it doesn't continue anywhere from there. And the result looks like this. It returns 3 rows, which contains the full path, of course, with a more detailed data structure, more detailed hierarchy. There could be more rows, but with our simple example, the result looks like this. And when we compare it to graph database, you can notice that, well, in graph databases, the relationships are first-class citizens. That means we don't need to create any foreign keys like parent ID to be able to connect each other to them. It's effectively stored as a graph, which is represented by these lines, right? And if we are going to describe the same query in Cypher, we'll see that it's much easier to read. Well, the starting point is still similar. There is a where condition. And the recursion is hidden in this part that shows with the wildcard. It says that we want to traverse as long as possible. Of course, in a real case, it's sometimes useful to limit the length of the chain. But in this example, I'm going to show that it can be also unlimited. And the result, well, it's a path because we are returning a path from Cypher. And it shows the same results as before. Right. I can show it to you on the demo, just to be sure that we know what we are talking about. And yeah, this is the full hierarchy. And for example, in here we are showing the full path because, well, it can be any depth nested anywhere else. And here the path has length of 4 because there is, well, this is missing in the example. There is also a server which contains it. Okay. The second example that I prepared is visualizing the data flow, which is fairly simple when we visualize it on the low-level view, because when user chooses to start on the leaf asset, then, well, the traversal is simple. We are following the flow relationships, going from left to the other leaf asset and to the end leaf asset. And well, this is the traversal, how it really looks like. And but What we are supporting at MANTA also that user can select anything in the hierarchy, because maybe user is not concerned with the flow from the leaf assets like columns, but user might be concerned about showing the flows from a table or even from a database. So user chooses this leaf, which is not, well, it's not a leaf, it's a non-leaf asset, and he expects that the flows that are shown to him are actually on this level and not on the well, downmost level, because that might be too detailed. So the actual traversal needs to look like this. The query starts in here, in the starting point, goes down, follows the flow, then it needs to go up to the same level of detail that user have chosen, and then back down and follow the flows and back up. We are storing the flow relationships only on the downmost level because it's easier to manage the data, and it also helps us with flexibility of the queries, because we are experimenting with different kind of flows, and this way we can use the same data structure. All right, and in the example, I'll show you the difference. Either user can select this column and visualize it. Then he sees that this column fee amount goes to another column in a talent ETL. But it's the lowest level. But also user can select the table and visualize the table. And now it's visualized that, well, there are no columns, but then user can expand it and see that actually inside there are multiple flows, and by default the visualization connects all them together so that the view for them is much simpler to understand. And well, that's about it. We showed you how data lineage for us, it's a map of the full environment of the customer's databases, ETLs, reporting tools, basically all the computations and data, how they manage it. MANTA is able to scan the whole environment with only access to the databases and potential also source codes like SQL DDLs or stored procedures. And based on this information, MANTA can show the visualization of the environment. And the reasons why MANTA uses Graph Database are for performance and for flexibility of the queries, so that we are not restricted by relation to databases. Thank you.
Yeah, thank you, Jan. And
I'm sorry.
Okay, go
I
on.
have one more note. I promised to my young sons to say hi to them because they are watching me. So, hi, Adam. Hi, David. Hi, David. And this is all from me.
All right. So,
Okay.
Thank you for your attention. We are prepared for questions, if you have
Okay,
some.
so first we're going to go to the online questions. We have first question. Does your software support database clusters or even multi-region clusters?
Let's say it's like does not that much connected with the clusters. Let's say we can scan their schemas. So their deployment setup, it's not that much interesting for us. Have you heard about this case?
Well, it depends whether the question is about scanning a database cluster or whether it's about scaling up the MANTA itself. Is it clear from the question?
Oh yeah.
Well, we support scanning the clusters because, well, when we connect to any replica of the cluster, we can read the metadata, which is usually the same across the cluster, or we could connect to multiple replicas of the cluster.
He is asking about scanning clusters itself.
Oh, yeah.
Then I would say we support it.
Yeah, we support it, but the deployment setup is not we really deal with. So we just scan it, and the deployment doesn't matter that much.
Okay, thanks. And here is the next one. It's rather long, so bear with me. I realize it is a separate topic, but just a quick question about AST generation. How is the garbage in the existing databases, tables or fields that exist there for whatever legacy reason, but are not used, dealt with? Is there some discovery tool to help with it, or is it entirely manual?
Yeah, I hope that I get the question. I'm not sure if I get it correctly. So again, we are scanning the AST3. It's our middle product. So we do a lot of filtering from it. Just there is and I have heard the word garbage.
Yeah, garbage. Yeah.
And just not sure if what kind of garbage is this, but when we scan the source code, we use, let's say, from 10 to 20% of actual script. The other things we filter out. So, and those data we store then to the database. If we talk about the garbage, which is actually stored in the database, like a customer's data, we don't watch them. We don't scan those data. Just the schemas, that's the things for us. I hope I answered it and I got it right.
Yes, you got it right.
All
okay. Here, audience in Zagreb, are there any questions? If you have to raise a hand. Okay, here is the mic.
Thanks. Okay, I had two questions, actually. First is, how do you deal with data lakes, since the data lakes are pretty much consist of unstructured data, and data lineage and generally metadata in data lakes is a quite hot topic and can be a huge burden on the data lakes. And the second one, how do you deal with semi-structured data?
Semi-structured?
Semi-structured. Semi-structured.
Semi-structured data.
So JSON and XML.
Yeah.
So that's the second and first is about data lake.
Yeah. The first of all, we cannot scan everything. We still develop the new scanners. So when we have new customer with new requirements, we do some custom development for him. Then we have to admit that sometimes it's super hard to connect the data between several systems. And in that case, our customer success team must go in the place, they check the data, do some manual mapping, and connect the data manually, simply manually, because not everything, and I hope I mentioned it, it's not possible automatized. And of course, we took some experience from their work for customers, and we think, okay, can we create something clever for next time? Sometimes it's possible, sometimes not. I hope I at least partly answer your question.
I might have one thing to add to David. We have a special algorithm that we call it restriction algorithm that allows us when there is data that, for example, there is one large table that connects everything together, and when user would visualize it, then everything would lead to a single table, and then going from it to somewhere else again. We can put special restrictions on assets so that the algorithm knows how to avoid this problem, so that it can show the flows from the source to target, and not through everything, but only the real source and real target. For example, if there is a column that contains the name of source table and target table, and it's a logging table that logs everything, then we can avoid the mess and make the flows more useful for the user.
Any more questions from the audience here in Zagreb? Just one more.
Hi guys. So my question exactly is, so let's say if we have the simplest scenario, and then are you having some automated way to detect which columns from one system are going into another system? I get if you have 50 scanners, that's a quadratic amount of how do you detect that, but is there some way how to connect them automatically?
Yeah, just we use several kind of methods. The first one, it's very obvious. It's by name. And then we trying to do some tricks. You know, a lot of names are similar, or there is some, you know, dictionary, the substitutes, and so on. We also wanted to experiment. There's just idea with some AI or something. Yeah, just fairly simple way to connect it.
Yeah, Memgraph has link prediction, so try that.
Yeah, thank you. Thank you for that recommendation.
Yeah, one more question. Let's say someone alters the table or something. Like, how do you scan tables again? Do you do some batch jobs, or how often is that rechecked?
Yeah, that would be a very good question to my colleague who is really in charge of that. But I'm afraid right now I'm not sure if we do this, if we do the batch jobs. So remember that.
Usually, users can run the scan manually, but maybe there is also a possibility to run it automatically every week or so. I'm not sure if we support it in the UI, but it's definitely possible to script it.
Oh, yeah, that makes sense. And do you also scan store procedures, triggers, like to detect,
Yes.
let's say, between views and stuff? Yeah.
Yeah.
Including the flows that goes, how it goes from inside to any other procedures.
Yeah, exactly.
Okay. Any more questions from the audience? No? Okay. Thank you, guys. Thank you for coming to Zagreb, to our meetup.
Thank you.